My name is Mihai, and I'm the founder and CEO of a company called Cyberstorm. At Cyberstorm, we and other small companies such as Intel or Samsung, we truly believe that the future of AI is going to be represented by the neuromorphic computing. And today I'm going to try to give you a short overview, a short introduction in what neuromorphic computing is and how this technology will profoundly impact our daily lives in the future. Shit. All right. So neuromorphic computing, simply put, as the name suggests, uses a model, a hardware model, which is inspired by the workings of the brain. It is based on a novel electronic component called a memory star. And while the memory star name by itself, it means that it's a resistance with some kind of memory. A memory star is much more than that, actually. And we are going to see a little bit later how this new type of electronic component will create a paradigm shift actually in the next few years. Memory stars are basically small electronic components. Right now in the world we have transistors. Everything around us is based on transistors. We have other electronic components such as diodes, capacitors. The memory stars were theorized in 1970s by a guy called Leon Chua, and they were manufactured for the first time in 2011 at HP Labs in US. The memory stores actually, they are able to remember somehow what is happening to them, what is happening with them, and this makes them very interesting in developing and building new types of computing architecture, a traditional non-von Neumann architecture. Every computing architecture that we are using right now is more or less a von Neumann architecture. And memory stars have these unique characteristics which can transform them into something slightly different, more natural, more similar to the way in which nature is computing in a way. Memory stores, in the end, are very good for a lot of things. We developed a cybersecurity solution for that because they behave in a non-linear way, meaning that their behavior in time is impossible to predict. And of course, they are very good, and they are going to power up the neuromorphic computers of the future. And the big difference between these computers and the current architectures is the fact that they are going to be able to sustain a lot of parallel operations. In memory computing, it's already doable, and they are extremely efficient from an energy point of view. And of course, outside we have a small booth, and where you can see that how we are using them for pattern recognition. I'm going to have a small adjustment here. Their power consumption varies. It's something in the ranges between 1 nanowatt and 1 microwatt. So we are able to develop pattern recognition models which have an insignificant power consumption. And this makes them perfect for the edge, for any kind of other new devices out there. And remember that in the next, 10 years, 26 billion new IoT devices are going to be manufactured. So if we would like to have AI on the edge, most likely we are going to use this kind of neuromorphic computing architectures. First of all, I would like to let's dive a little bit into history. The first computers in the world were actually analog computers. But because mankind wanted to go to the moon, it was very hard, if not an impossible task, to deploy a huge computer on that small space shuttle. And the first digital computers, the computers based on transistors, actually achieved that task of navigating towards the moon quite easily. And that's how this huge IT&C industry started to appear. But right now, current computing architectures and current technologies, they do have some very severe limits. And those limits are we are actually fast approaching those limits. And I'm going to shortly explain why this is happening and why, again, neuromorphic computing and probably quantum computing in the future are going to become viable alternatives to what we currently have. This clicker is bad. Sorry, it's about the clicker anyway. Simply put, right now we have some issues. As you probably know, every kind of chip is being manufactured on silicon. And in silicon, we have Moore's law, which stated that every couple of years, the number of transistors crammed on the surface of the silicon is going to double. Moore's law is near its end. As NVIDIA CEO actually stated, we can keep shrinking transistors, but we cannot shrink atoms. So we need to take into consideration materials physics and to find other ways of manufacturing, alternative ways of computing. And there is a very big pressure right now because what's happening in the world is quite simple. We can only manufacture advanced chips in one country in the world, and that's Taiwan. And to manufacture those chips, we need one of those ASML machines, which are very expensive, and usually a foundry costs north of $20 billion. And we simply put, we don't have enough of them in the world. That's why we decided that in the beginning, 5 years ago, when we started our own R&D within the company, that we should look at other types of materials. And the most obvious material for us was a material called IXO. Everyone has this kind of material inside your own pocket, because it's the same material from which the mobile phone screens and LCD screens are made of. And we try to move away from the silicon. Silicon itself, advanced manufacturing nodes, 3 nanometers, 5 nanometer process nodes, they do pose a lot of challenges. And simply put, we cannot really put an infinite number of transistors there, while keeping also the power consumption at a decent level. And if we are going to talk about the edge, about IoT, about EVs in the end, we need some kind of computational power, but we don't have that computational power at the moment. And we don't have the required power consumption to deploy those architectures on the current IoT devices. And that's why, for us, in the beginning, it was quite obvious that we should look at different types of materials. Because in the end, an electronic display, a mobile phone display, is still an electronic circuit, right? Right now, in the current semiconductor industry, we have some huge challenges. And some of these challenges are quite obvious, because from a geopolitical point of view, manufacturing 95% of all the advanced chips in the world in one single country, it's a big risk. The semiconductor industry, it's near its current limits. Moore's law is near its end, and Zener scaling actually ended close to 10 years ago. Zener scaling is very important because it has a direct connection between the size of the transistors and their power output, the power consumption. So for 10 years, we are not able to increase the efficiency of our current chips. And that's why we need to look somewhere elsewhere. Quantum computing is still some years away in the future. And the most readily available, the technology which is closest to market right now is neuromorphic computing. And neuromorphic computing will represent a paradigm shift because it will change the way we are going to develop our hardware, our electronics, and even our software. It will drastically change the way. According to Gartner, of course, neuromorphic computing is actually the future of AI and is being considered the number one disruption right now in the world. Neuromorphic computing actually represents an alternative. It's working right now. Quantum computing is not working yet. We have some issues there. We have some problems there. We don't know. In quantum physics, there are some uncertain things. We don't know if gravity impacts quantum mechanics. We know that in theory it should. And quantum computers are very hard to manufacture and to scale. We are not going to have a portable quantum computer, by no means. But we can have, we already have neuromorphic computers. Outside, you are going to find this kind of prototype of a neuromorphic computer anyway. Right now, one of the main factors for which this kind of computing paradigm shift is going to happen is happening because of AI. And if we are going to develop more natural algorithms, more efficient algorithms, while keeping the power consumption at a decent level, we need to do something different. Initially, as you see, we first had GPU-centric. The architecture was centered around GPUs. After that, on ASICs. The third wave is going to be neuromorphic computing, because neuromorphic computing has a huge advantage. It acts, a neuromorphic chip, it will act both as a CPU, as a memory, and as a storage at the same time, in the same place. So we can achieve more with a smaller number of, let's say, memory stars, of a smaller number of neurons. So this is why neuromorphic computing is quite close to the market entry. Here you are going to see a comparison between von Neumann architectures and neuromorphic architectures. The most important one right now we are using this kind of sequential processing, right? Computation and memory is happening in different spaces, in different places, while in nature everything is happening in the same time, in the same place. Nature, our brains, biological brains, compute in a totally different way. Biological brains are not that good at multiplying matrices, right? But they are pretty good at coordinating lots of things at the same time, while being extremely energy efficient. And one of the most important things that we are going to escape binary mathematics anyway. We don't need to stay in the binary mathematics, which means that a lot of new options are emerging as we speak. Right now, in the current world, software actually does the hard work, right? Because we are designing machine learning algorithms, which are mathematical representations of what's happening, describing, and what's happening in nature. Neuromorphic computing actually changes a little bit the way, because the software itself is being represented by the electric power, characteristics of the electric power. So that's why it's a paradigm shift. It will happen, we are going to program things, we are going to make them think in a totally different way, in a more natural way. And this actually changes a lot of things. For example, we can train those memory stores to recognize some things in something like 5 milliseconds, while keeping the energy consumption as low as possible. Neuromorphic computing has, of course, some interesting advantages. They're naturally sustainable because their power consumption is very low. So it will make more sense to use them on IoT devices. We can train them with small or limited data sets, and they don't require an internet or cloud connectivity. And we actually created adaptive systems. They can adapt in real time to their environment while being in a black box, I think in the end. They don't need an internet connection. Outside, we are going to find on our small booth a small demo. It's the first demo out of several other demos, which are going to showcase more and more the impact of the technology and how we are going to use and how we are using these memory stores to create a small paradigm shift, I think, in the end. The next step for us, it will be to create something like an artificial ant brain, because ants are very interesting for us. They can navigate easily. They only have something like 17,000 neurons, and they can navigate pretty good, in a pretty good way. They are very efficient, and their sheer number makes them perfect for certain use cases. Of course, in the future, we are going to achieve something very similar to a positronic brain. If you know about Asimov's positronic brains, probably that's the path. I'm not sure if we are going to be able to achieve that during our lifetime, but from an evolutionary point of view, it made more sense for us to focus a little bit on the ants. Because ants, we can create this kind of swarms which are going to be deployed on other things, right? And if you can imagine that IoT devices are swarms in a way, somehow, and that's why we focused a little bit on these ant brains. Our approach, of course, was to use that thing, was to create something like a chip, but it's not actually something like a chip on a new type of material. We started our own research 5 years ago. We chose IXO. We patented this technology throughout the world. The patent was granted at some point in time, and based on that, we started developing our solution. The idea from the start was to have this option of moving away from the silicon. Silicon is nice, we are still going to use it, but we weren't sure back then that in 10, 15 years we are still going to use silicon. And that's why our approach was to move away. And we realized that right now in the world, there are, I don't know, 4 or 5 foundries which can manufacture chips on a 5 nanometer process node, but there are something like 20,000 display factories which can manufacture this kind of chips much more cheaper. And those factories are working right now, and they can be, and this kind of chips can be retrofitted to any kind of current existing digital technology. Yeah. Outside, you are going to see an analog pattern recognition device. It wasn't my name, it was my colleague's decision to name that thing like that. But it's actually working. It's not a big technological demo. It's more like a technological showcase. But you are going to see that they are able to recognize some things at the circuit speed, more or less light speed, while keeping the power consumption very low. We can recognize numbers, letters, and a lot of other things right now. And we are slowly moving towards far more complex patterns and algorithms. Of course, in order to work with these analog devices, we needed to have a digital counterpart. And that's why we designed, because we are partners with ARM, we designed our own ARM coprocessor in order to be able to work with these memory stores. And that's why I personally believe that in the future, we are going to use a mix between current architectures and something neuromorphic or analog. The idea is that we are right now building the first blocks, which are going to end up in a technology very similar to what Robot Daniel Olivo from Asimov's foundation looks like. And it's quite simple, because the current world, it's closing. In today's world, we have a lot of challenges. Energy consumption, it's an issue. Manufacturing chips, it's an issue. IoT devices need also a chip with a small, I don't know, very efficient chips, right? And at the same time, we need to produce them in vast numbers. We cannot really produce them in vast numbers because we don't have enough places in the world in which to produce these chips. But there are alternatives. And that's why these alternatives, we are building those alternatives, and we are building these small blocks. These small blocks can be, these small blocks can be very easily manufactured even right now. So we can, right now we can manufacture chips which are not built on silicon anyway. I think that we strongly believe within our team that what we are building is going to somehow change some things. The main challenge that we have today is the fact that we are living in a digital framework. We are used on working with von Neumann computers. We sometimes forget the fact that nature is not digital. Nature is analog. And the reason for which nature managed to remain on this planet for more than 1 billion years, it's quite simple. It's anti-fragile, right? It's sustainable. It has a low energy. Yeah, maybe we cannot easily make complex mathematical calculations using our brains. But nature itself is very sustainable. And if we are going to have something which resembles AI, I'm pretty sure that we are not going to have that AI on a digital system. We need this kind, the material itself needs to have this kind of neuroplasticity anyway. Because everything in nature has these things. So we need to get inspired from the nature. We need to take some inspiration, and we need to think about new ways in which we should develop our electronics. Right now, chips and electronics are being built with some very particular functionalities from the beginning, right? But in nature does these things in a slightly different way. And I personally believe that the mix between our current architectures and a more natural way will change a little bit, will change and will create a paradigm shift. And of course, you don't have to believe me. You just need to visit us there. You need to wait for Intel, probably the other small company which is going to launch these kind of neuromorphic chips. But it will happen. It will surely happen. That's the wrong operating system. Anyway, I would like to thank you for your time, and if you have any kind of questions, bring it on. Thank you. Shoot. Yeah. We are creating our own types of software, but if you have any kind of ideas about new types of the current software can be used, yeah. Long story short, yes. Yeah. Long, the short answer is yes. Of course, you can see that I have one of these things here. It's already been working for 2 years. We don't know why, but that's a recurrent event within our office. Some things are working, and we don't have any kind of idea why they are working. But of course, if you like to talk, to speak with us, and if you like to have to learn more about that, we are outside. We have this guy which is going to be able to answer to any kind of technical questions. And yeah, hopefully you are going to help us. You are going to help us, and maybe you can have a lot of ideas about how we can use these things. We have some ideas, but we are totally sure that some 90% of the solutions are going to come from you. Thank you.